Hello everyone, I'm Guna Prasad from the University of Washington. Today I will be presenting our paper titled Handling Highly Contended OLTP Workloads Using Fast Dynamic Partitioning. And this is joint work with Alvin Chong from UC Berkeley and Dan Suchio from the University of Washington. With the advent of cheap memory and multicore machines, multicore main memory architectures have become the norm today. However, conventional database software was designed for single processor machines, so they could not scale well on modern hardware. While many old bottlenecks such as disk latency have been removed, concurrency control has become the new bottleneck for OLTP performance. Hence, the past decade of OLTP research has largely focused on bridging this gap between hardware and database software. These improvements, however, are not uniform across the board, primarily depending on contention in the workload. Contention is a measure of skew in the data access pattern. Higher the skew, higher the contention, in which case a lot of transactions tend to access a small set of hot data items. Fundamentally, lower contention means fewer conflicts and hence better data parallelism. Research in this space has resulted in wild success, in some cases scaling up to thousands of cores. Higher contention, on the other hand, stresses shared memory concurrency. Pessimistic approaches suffer from issues such as lock thrashing or deadlock handling, while optimistic approaches usually have inflated abort rates. Overall, shared memory approaches have largely been unsuccessful for high contention workloads. In the partitioned approach, we partition the database and execute transactions that belong to a single partition on the same core, serially without any concurrency control. This is a promising approach to handle high contention workload and best when possible. However, performance almost nosedives when there are cross-partition transactions, that is, transactions that access data from more than one data partition. Moreover, hot data items could be unevenly distributed across these partitions, leading to imbalance and poor performance. Naturally, since this approach depends on a static partition assumption, workloads where hot data items change over time are a challenge, especially in today's TikTok world where videos could go viral in under a few seconds. These challenges bring us to today's talk. We introduce our system Strife. Strife is a hybrid between shared everything and partitioned approaches, combining the benefits of both. It mostly avoids concurrency control by scheduling transactions intelligently and adopts to a dynamically varying hot set. There are three key assumptions in the Strife model. 1. Transactions are executed as stored procedures. 2. The read-write set of transactions can be determined statically. Whenever not possible, we could still execute them using a reconnaissance query like systems in deterministic concurrency control. Finally, Strife adopts the batched execution model in which transactions are collected together and executed in small batches. Note that this is not entirely new. Systems such as Calvin make a similar assumption, and this is also typically the user model in group commit-based systems. In Strife, say we collect a batch of transactions T1 to T6 along with their read-write sets. We visualize it using its access graph, which is a bipartite graph where on the left you have the data items and on the right are transactions and edges represent access. Note that we do not include read-only data items in the access graph since there is no need for concurrency control to access them. Strife fundamentally depends on the following insight. If you look at transactions T1 and T2, they access common data items and hence conflict with each other. So in order to execute them without concurrency control, we need to do it on a single core. On the other hand, between transactions T2 and T3, there is no conflict, so you can execute them on different cores without any concurrency control. If we were to follow a naive clustering scheme, we would cluster T1, T2, T6 into one and the remaining into another cluster. And since these two clusters are conflict-free, you can execute them without any concurrency control on two cores. However, life isn't that easy. Sometimes there are transactions such as T1, T7, and T8 that access data items across these largely disjoint clusters. Following our naive clustering scheme, we only have a single conflict-free cluster, and that reduces our parallelism significantly. In Strife, we identify these transactions as outliers, and we put them into a separate residual cluster as follows. This way, the remaining batch can be clustered into two conflict-free clusters, and thus exploiting more parallelism. This brings us to the Strife execution scheme. A batch of transactions is executed in three synchronous phases. First, it is analyzed. Then conflict-free clusters are executed on multiple cores without any concurrency control. And then residuals are executed on all cores with concurrency control. For instance, in our current example with two cores, first the analysis phase is executed. Note that the cores that finish early wait for other cores to finish the phase before proceeding forward. Then conflict-free clusters are executed without any concurrency control, and then residuals are executed. The same process repeats for the next batch. An important question to answer here is how many residuals turn off. When we set residuals to 0, it reduces parallelism excessively. On the other extreme, if we cluster all transactions as residuals, it resembles traditional shared everything OLTP. So Strife uses a heuristic that restricts residuals to a fraction alpha of the batch size. This is currently user supplied and can be learned if necessary. So our core clustering problem is as follows. Given a batch of transactions P, we want to partition it into clusters C1 to Cn and R such that there are no conflict between transactions in Ci and Cj, and size of R is less than alpha times the size of P. Now there are a couple of challenges here. Firstly, our clustering problem is akin to graph partitioning, which is fundamentally an NP-hard problem. On top of that, we also need to separate out the outliers that we identified in the last section. Moreover, we need a way to do all this efficiently and in parallel. We iterated over a number of existing solutions, but all of these solutions either resulted in poor clusters, were computationally expensive, or could not be parallelized easily. Note that this also includes techniques from the automatic database partitioning literature, since they were primarily designed for offline processing. So we came up with our own solution. Let's look at our solution using the TPCC example. The figure on the right depicts the access graph for a batch of new order transactions. Each transaction in the middle updates a warehouse on the right and one or more stocks on the left. We identify hot items in the batch using random sampling and create what are called seed clusters. We do this as follows. We first sample a transaction at random. If no data item it access belongs to a seed cluster, then we create a new seed cluster and merge all connected data items into the seed cluster. We sample the next. Again, none of the data items here are connected to any seed cluster, so we merge and create a new seed cluster. If we sample a transaction that touches a data item already allotted to a seed cluster, for example, in this case, we simply reject it and continue. We repeat this rejection sampling technique for k times. The parameter k is typically a constant times the core count. A few things to note here about the seed clusters. With a high probability, we will identify the hot data items in the batch due to the randomness of our sampling. And suppose there are n hot data items d1 to dn, which are almost independently accessed, then with high probability, we will create a seed cluster for each one of them. In the next step, we grow these seed clusters without merging them. In our example, this would be akin to growing the seed warehouse clusters to include all the stocks that belong to the warehouse. We do this by scanning transactions one by one, and whenever all data items are unallocated or belong to the same seed cluster, we merge them into the same seed cluster. When they belong to more than one unique seed cluster, we simply tag that as a residual and move on. In this figure, the residuals are denoted by a black dot. Now, in some cases, the seed clusters may result in a large number of residuals. For example, warehouses 2 and 3 in this figure. So we merge pairs of seed clusters based on the number of residuals resulting due to the two of them. And that concludes our algorithm. Overall, the algorithm is quite efficient. It executes in linear time on the batch size in as low as 3 passes over the read-write sets. A note on parallel clustering. Our algorithm heavily leverages the union-find data structure to maintain and merge data nodes together. We custom designed a concurrent version of the union-find algorithm to exploit intra-batch parallelism. This improves throughput and latency, yielding almost linear scalability. You can find more interesting details about the algorithm and its implementation in the paper. Now we present our empirical evaluation. The experimental setup is as follows. All our experiments are done on a multi-socket Intel Xeon CPU with 2 sockets and 15 physical cores each, with hyperthreading disabled. We obtain baselines from authors whenever possible and use a batch size of 10,000 transactions for all our experiments. We present 4 themes of evaluation here. First, we compare Strife to shared everything protocols, then with high contention proposals from the literature, then on a time-varying workload, and finally, evaluate its performance across contention spectrum. Here, we compare Strife with popular shared everything protocols that are representative of variants of 2PL and Silo for optimistic concurrency control. The plot here depicts throughput in millions of transactions per second versus number of cores on the TPCC workload with 4 warehouses. Firstly, it identifies all 4 warehouses as conflict-free clusters. We also see the performance of Strife almost double from 2 to 4 cores as expected due to increased parallelism in the conflict-free phase. The marginal improvement after 4 cores is only due to increased parallelism and analysis phase. Depending on the protocol, all others suffered either from lock thrashing, deadlock handling, or inflated abort rates. Now we look at the hot benchmark. In this benchmark, each transaction performs random read-write access on 10 records, out of which 1 is hot and the 9 others are cold. The hot data item is chosen randomly for 100 data items. We again report the throughput as we increase the number of cores. Strife identifies approximately 60 conflict-free clusters with k equal to 100. Analysis shows that 40% is spent on analysis phase, 50% on conflict-free phase, and remaining on residual phase. Since we have a lot of conflict-free clusters, there is increased parallelism in conflict-free phase and hence scales almost linearly up to 30 cores. All the other protocols are seen to flatten after a certain number of cores. Now we compare Strife with the following proposals for high contention OLTP. MOCC is a shared everything optimistic protocol that uses locks for hot records based on temperature statistics. PartCC is a partition database that acquires partition level locks. DORA is an alternate architecture that adopts thread to data assignment over thread to transactions. Transactions move across cores, acquiring and release or locks to perform concurrency control. Finally, Authors is an alternate architecture as well that adopts static partitioning of concurrency control on a dedicated set of threads and uses message passing between execution and concurrency control threads for scalable lock acquisition and release. The plot here depicts performance against the number of cores. Note that we set the number of partitions to same as number of cores. Some baselines require that. Strife is better than MOCC due to its shared memory concurrency overhead. It is also better than Authors since async message passing for locks increases lock hold times and stresses high contention even further. DORA and PartCC, however, successfully exploit the static knowledge about partitions. On the other hand, Strife rediscovers these static partitions every time and hence incurs 40 to 50% overhead. With smaller number of cores though, Strife performs similar to PartCC and Dora since the effect of cross-partition transactions are higher. Now let's compare these on our hot benchmark. The 100 hot records are evenly distributed across these partitions and cold records are chosen at random from 3 partitions. In this plot, we depict throughput as we vary core or partition count. Strife outperforms all the other systems. Authors Dora and PartCC, those that depend on a static partition, suffer a lot due to cross-partition transactions. In the third experiment, we use a time-varying workload created using the hot benchmark. The plot here depicts throughput in millions of transactions per second versus time as we vary the set of hot records every 30 seconds. These hot records may be unevenly distributed across these partitions over time. As we can see, Strife and MOCC are resilient to such a time-varying workload, with Strife almost 2x better than MOCC. Dora, PartCC, and Orthres suffer greatly due to cross-partition transactions, and their performance also varies depending on how the hot items are distributed. Overall, Strife outperforms all protocols, adapting very well to time-varying hot set. Finally, evaluate the performance of Strife and other baselines as we vary contention. Even though Strife was not designed for low contention, this experiment helps us understand its behavior further. We do this on a partitionable YCSP workload, which uses a Zipfian distribution. We vary theta of the distribution that controls contention. As you can see, Strife is not universally better. For low contention, silo and no wait are better since concurrency control overhead is quite low under low contention. Under high contention, analyzing the patch for conflict-free clusters is better than doing concurrency control. That brings us to the end of my presentation. To conclude, we introduced Strife, which is a transaction processing protocol for high contention. It identifies hot records during runtime, clusters conflicting transactions together, and executes them mostly without any concurrency control. It yields substantial performance improvement over traditional protocols on high contention workloads. While it incurs a 50% overhead compared to partitioned approaches for statically partitionable workloads, it improves performance by up to 2.5x when such a static partitioning is not viable or when the hot set varies over time. Thank you.